In this video, I want to talk about something so powerful, and that is the work energy theorem. So I'll start with the question of why is it even important to know the net work done on an object? Okay, what difference does it make? What does it get us in the real world that allows us to know more about an object, to make predictions about the future, to do science things? And the truth of the matter is, I had said that work is something that gives an object the currency of energy, right? One of those currencies that work gives an object is kinetic energy, okay? So it turns out that the work done on an object, specifically the net work done on an object, okay, is equal to the change in kinetic energy that object experiences, all right? So this is a famous theorem from which you can make lots of predictions called the work energy theorem. Okay, and to state it again, I'm saying that the net work done on any object is always equal to its change in kinetic energy, okay? Which is, of course, its final kinetic energy, or Ke2, minus its initial kinetic energy 1, right? So when forces combine to do some overall amount of work on an object, right, that's going to typically change the kinetic energy of the object, and that has to be constant. This is, in a way, an expression of conservation of energy. The amount of work done on an object must be equal to the change in energy of that object, okay? All right, so let's, as always, see this in practice. What does this actually look like? Okay, so if you guys can go to the next slide that says magical falling cats. You guys have probably seen this. It's really cool. Cats always fall on their feet. There are some scientific reasons for this, some physics-based scientific reasons, which I'll share with you at some point in the future. But for now, we're just going to look at this problem. Cats are infamous for being able to land on their feet, regardless of the position from which they fall. Let's suppose that there is a 5.56 kilogram cat falling from a 4-meter branch who miraculously, as always, lands on his feet. On the way down, the cat also experiences an average drag force of 1.1 newtons, right? So if we look at this cat, something like that, right? And we draw a free body diagram for this cat, we know that there is, of course, a weight going down, right? Gravity's acting down and pulling this cat down. And then we also have a drag force, which we'll call D, okay? Remember, there is some work being done on this cat for each force, okay? So if we want to find the net force in this case, right, that's going to be, or sorry, not the net force, the net work. It's going to be the work done by gravity, right, plus the work done by the drag force, okay? So let's find out what these are. First of all, work done by gravity. Remember, work in general is F dot D, right? Okay, but gravity, the gravitational force is mg, right? So that's going to be mg d, and the dot means the cosine of the angle between them, right? So what is the angle between cosine and the, force and the displacement? Well, force is going down and the cat is falling straight down. So the angle between those is 0, right? They're in the same exact direction. So cosine of 0 is always just 1, right? That makes that really easy. So I can just go ahead and say that the work done by gravity is equal to the mass of the cat, which is 5.56, times gravity, which is 9.8, times the displacement, which the branch is 4 meters high and it's falling to the ground, so that's just going to be 4 meters. Okay, I put that all together and I get a work due to gravity of 218 joules. Okay, so far so good? All right, so 218 joules, we can go ahead and put that over here. Okay, now I'm going to erase this so I can go ahead and have room to calculate the work due to that drag force. What is that work due to drag? Okay, well, let's see here. We know, once again, that work is equal to force dot displacement, right? The force vector dotted scalar product with displacement. And that, in this case, is going to be the drag force times the displacement times the cosine of the angle between them. Once again, this time, however, drag is up, but displacement's down. That is an angle of 180 degrees, right? And so that means that the work due to the drag force will be the drag force, which is 1.1, times the displacement, which again is 4, right? Times cosine of 180 degrees. And as you guys know, that is negative. So the work due to drag in this case is actually a negative work, becomes negative 4.4 joules again, right? So I want to add that negative 4.4 over here to get 4.4 joules. So the net work is the sum of these two things. If I add these together, I believe I get 213.6 joules, okay? So the net work is 213.6 joules, okay? That's part A. We found the net work. Part B is asking us what is the change in kinetic energy of the cat as he falls from this branch. You know, how much currency does that work give him, okay, in terms of energy, right? Well, it turns out this is where the work energy theorem comes in and just does all the work for us. And this is why it's so beautiful. We can say, so if we want to find the change in kinetic energy of that cat, okay, we know it simply has to be equal to the net work, which we just found, guys, right? So the change in kinetic energy is the work net, which is 213.6 joules, right? Okay, easy breezy. That's part B. We're totally able to steal that, right? Okay, the next question is, how fast is the cat going before it hits the ground? And this is where the work energy theorem gets really cool, because it can predict the future. It can basically erase all that hard work that you had to do with kinematics. I don't think it's that hard of work, and I think you guys got pretty good at it. But it can erase the work that you did with kinematics simply because now that we know the change in kinetic energy, it's very, very easy to find the velocity just before the cat hit the ground. How so? Well, change in kinetic energy, remember, is just the final kinetic energy minus the initial kinetic energy, right? This is the kinetic energy just before he hit the ground, the cat. This is the kinetic energy that he started with. He was just sitting there up on a tree, not moving. That's 0, right? And that difference has to be 213.6. We already calculated it, right? That means that 1/2 mv squared, right, where v is the velocity just before he hits the ground, right, is simply equal to 213.6, okay? I put my mass of my cat in, which is just 5.56. So I'll put 5.56 in for this, kilograms, okay? And then I solve for V2, just a little bit of algebra, multiply by 2, divide by the mass, take the square root, and I get 8.8 meters per second. That's how fast this cat is going just before he hits the ground, but it's okay because he lands on his feet, as all cats do, okay? So the point of this problem is to demonstrate the work energy theorem, right? This is just a classic example of how I can use the work energy theorem to find the change in kinetic energy of an object, right? And to also find and predict the velocity of that object after the forces have acted on it, okay? And this is one of the powerful aspects of energy, right? It almost lets you do away with all the kinematic stuff that we've learned before and take this totally different way to get the same answer. I encourage you guys to use a laundry list and see if you get the same number, okay? With that said, in the future, we're gonna take this one step farther and use conservation of energy in order to get the same results.